Welcome back to Very Ordinary Differential Equations. Here we're going to begin a review of properties of series. This is not intended to be how you learn about series for the first time, rather a review if you already sort of know it. Well, what's a sequence? A sequence of numbers is a list x sub 0, also pronounced x naught, x1, x2, etc. Each of them has to be a real number. We're talking about sequences of real numbers here. The number I is called the index of the term xi. So if I refer to the index of something, I mean that subscript. Usually, the numbers in a sequence are going to be given by some sort of explicit formula. For example, x sub I could be 3i minus 1, in which case, if I is 0, we get x naught equals negative 1. When I is 1, we get x sub 1 equals 2. When I is 2, we get x sub 2 equals 5, and so forth. But honestly, any list of numbers can be considered as a sequence, whether it's given by an explicit formula or not. Sometimes we're going to use an index starting not at 0, but starting at 1. So instead of indexing over the natural numbers, which begin at 0, we will index using positive integers, which begin at 1. The only distinction there is whether the sequence begins with x naught or begins with x1. Suppose you have a sequence, possibly indexed over the natural numbers or the positive integers. We'll say that the sequence has limit L if for any positive number epsilon, which we will generally think of as being very small, there is correspondingly some choice of index, capital N, again probably very large, so that for any index past n, the distance from x sub n minus L is less than epsilon. If this happens, we will write that the limit, as I tends to infinity of xi, equals L. In other words, no matter how small of an epsilon we pick, as long as it's not 0, but a very, very tiny positive number, so regardless of which epsilon we pick, there is an index past which every term of the sequence is within distance epsilon of L. So the terms of the sequence do not have to equal L. This distance doesn't have to be 0, but no matter how close we want it to be, no matter how small we want this distance to be, there is an index past which the distance is less than epsilon. Suppose you have a sequence, and we'll just pretend it's indexed over the natural numbers. It's not a huge distinction. We're going to create a new sequence of capital S, where S naught is the same as x naught, but then S1 is x naught plus x1. S2 is x naught plus x1 plus x2. S3 is x naught plus x1 plus x2 plus x3, and so forth and so forth. Observe as well that Sn is the previous s plus the next x. So S naught is just x naught by default. S1 is x naught, but that's the same thing as S naught. So this is S naught plus x1. S2 is now these two things added together, but these two added together is exactly S1. So S2 is S1 plus x2, and so forth. If this new sequence of capital S's, of sums of x's, has limit L, well then we would write the limit of Sn equals L. But observe that Sn is just a sum, as the index I goes from 0 and terminates at n of the x's. S1 is x naught plus x1 and then stops. S2 is x naught plus x1 plus x2 and then stops. So Sn is merely this partial sum, this finite sum. If the limit of these partial sums is L, we will write this here. The sum as I goes from 0 to infinity of xi is L. When typesetting makes it inconvenient to put this under and over information here, we might just write summation of xi. If you just see the sum of xi like this, it's understood that it's going to infinity, and it's either starting at 0 or 1, and it might not make a difference in a particular problem. Now this infinite sum on the right is called the series formed from the sequence of x's. A series may or may not converge, and if a series doesn't converge to a real number, we will say that that series diverges. Well, we can create a bunch of quick initial results about series and summation of sequences. Summation is a linear operator. If we happen to know that the series formed out of AI converges to capital A, and the series formed out of BI converges to capital B, in other words, we have two different series, both of which converge, then the sum of AI plus BI converges to capital A plus capital B, and for any constant C, the sum of C times AI converges to C times capital A. Now it's important to know that the series converge before attempting to apply these results. If these series on their own don't converge, it doesn't make any sense to say this equals that, because these things don't converge to anything on their own. So before you can use a linearity of summation, you need to know that the series you begin with are already converging. For example, it's possible to define AI and BI so that this series converges, but these on their own do not. So somehow it is possible for the sum of AI plus BI to converge, but the sum of AI to diverge and the sum of BI to diverge. The quickest way, by the way, is just to let every single AI be 1 and every single BI be minus 1. Then here you'd have 1 plus 1 plus 1 plus 1, etc. That diverges to infinity. Minus 1, minus 1, minus 1, minus 1 diverges to minus infinity. But since AI plus BI is always a 1, minus 1, or a 0, this is just a sum of a bunch of zeros and does converge. Okay, so the only point here is make sure you know that series converge before you start discussing results about these converging series. Well, what's a geometric sequence? A sequence, notice I'm not saying series, I'm saying a sequence. A sequence is called geometric if the ratio of two consecutive terms is constant. So for every I, xi plus 1 over xi is always r. The ratio of two consecutive terms is the same constant r. If this is true, well then xi plus 1 is just r times xi. So x1 is r times x naught, x2 is r times x1, which is r squared times x naught, x3 is r times x2, which is r cubed times x naught, and so forth. In general, x sub n is r to the n times x naught. So this is a geometric sequence. Every term is given by a power of r times whatever x naught is. If we were to replace x naught with some constant a, then a geometric sequence is given by a times r to the I. A times r to the 0 would just be a. Then ar squared, ar cubed, and so forth. So this is a geometric sequence. What about a geometric series? Well, if we form a series out of a geometric sequence, we get a geometric series. Remember, a geometric sequence has general form of ar to the I. So if I sum up ar to the I, we have a plus ar squared, and so forth and so forth. Now, without going through a proof, because remember, this is just a quick review, a geometric series with ratio r converges if and only if the absolute value of r is strictly less than 1, in which case it converges to exactly a over 1 minus r. This gives rise to something known as the geometric series test. So suppose we have a geometric series. So we are summing up as the index starts at 0 but then goes without end, some constant a times r to the I. This is equal to a over 1 minus r if and only if the absolute value of r is less than 1. If the absolute value of r is bigger than or equal to 1, then the geometric series diverges. This is a pretty easy test to apply. If you're staring at a geometric series, you simply ask, is the common ratio in absolute value less than 1 or not? Also, if the series does converge, you actually get exactly what it converges to, a over 1 minus r. But geometric series are extremely specific. It has to look like a fixed constant times some constant to the index I, and that's an extraordinarily specific form for a series to take, and it's rarely going to come up in exactly that form. There's another very fast convergence test known as the p-test. Suppose we have the sum of I to the p. I want to point out that this is not a geometric series. In a geometric series, you have some sort of constant raised to the index power, whereas here we have the index raised to a constant power. Well, this series converges exactly when p is less than minus 1 and diverges when p is bigger than or equal to minus 1. And again, we're not going to go over the proof of this. This is just a review. Now, this test is frequently written in a modified form. Instead of writing I to the p, you'll frequently see this written as 1 over I to the p. This just reverses positive versus negative exponents. So here, p is less than minus 1 is exactly the same as here, p being bigger than 1. Here, p being bigger than or equal to minus 1 is equivalent to this form with p being less than or equal to 1. So whichever form you're using, just make sure you know it. There's another test for series convergence known as the divergence test. If a series converges, then the sequence from which it was formed must converge, and specifically must converge to 0. So if the sum of a sequence is something, L, then the limit of that sequence has to be 0. Equivalently, if a sequence doesn't converge to 0, then the associated series doesn't converge to anything at all. So if the limit of the sequence isn't 0, then the series does not converge. This is known as the divergence test. It's pretty easy to apply, but it only can ever tell you that a series does not converge. If the sequence does not converge to 0, then the series does not converge. If the sequence does converge to 0, you cannot conclude anything from the divergence test. That's a very common error for beginning calculus students to make. If the sequence converges to 0, you don't conclude anything. If the sequence doesn't converge to 0, then the series must not converge to anything at all. That's the divergence test. Okay, so under no circumstances will the divergence test ever tell you that a series does converge. The divergence test can only tell you when the sequence doesn't converge to 0, possibly it converges to something else, or maybe it doesn't converge to anything, then the series does not converge. The only conclusion you ever get from the divergence test is the series does not converge. Another quick test is called the comparison test. Suppose I have two sequences, A0, A1, etc., and B0, B1, etc., that satisfy 0 is less than or equal to AI is less than or equal to BI. So the terms of my sequences are never negative, but AI is always less than or equal to BI. Then if BI converges as a series, so does AI. And if AI diverges as a series, so does BI. The comparison test is actually extremely useful. It does require, however, that all terms are non-negative and that I do have this inequality I can string between the two sequences. One way to think of this is, if you're adding up something smaller than a converging series, then you are also a converging series. But if you are adding up something bigger than a diverging series, then you are also a diverging series, assuming all terms are non-negative. Being smaller than a convergent series means you're also convergent. Being larger than a divergent series means you're also divergent. Okay. However, if the sum of BI diverges, you can't conclude anything about the sum of AI. Being smaller than something divergent is really no information at all. Similarly, if the sum of AI is known to converge, you can't actually conclude anything about the sum of BI. Being larger than a convergent series doesn't tell you anything. Another very powerful, very useful, and frequently used test is known as the limit comparison test. Suppose I have two sequences. AI is non-negative, BI is strictly positive because I'm about to take the limit of an associated sequence, AI over BI. I don't want to divide by 0, so BI had better be positive. And let's assume this limit exists and is some constant C. If C is positive and a real number, then either both series of AI and BI converge or both diverge. So if I can take this limit here and get a positive real number out, both series do the same thing. In practice, one of them will be very straightforward, like a P series or a geometric series, and the other will be something we're trying to claim something about. We can say something if C is 0. If this limit here is 0, well then, AI over BI tends to 0. In other words, AI is typically much smaller than BI. So if BI converges, AI converges. Being smaller than a converging series means you converge. If C is 0, in other words, AI is much smaller than BI, and if AI diverges, well then BI is even bigger than that, so if the sum of the AI diverges, then the sum of the BI diverges. If C is infinity, if this limit is infinite, and BI diverges, then the sum of AI also diverges. So AI over BI going to infinity would mean that AI is much bigger than BI. So if BI diverges and AI is bigger than that, the sum of AI also diverges. Similarly, if C goes to infinity, then AI is typically much bigger than BI. So if the series AI converges and BI is a lot smaller than that, the series of BI also converges. 9 times out of 10, this first one is how it pops up. the limit is a positive real number, and you simply conclude both series do the same thing. They both converge or they both diverge. However, if the limit is 0 or infinite, there is still some stuff you can say. And essentially, it boils down to this same argument of being smaller than a divergent series tells you nothing, but being smaller than a convergent series tells you you must converge. Similarly, being larger than a convergent series tells you nothing, but being larger than a divergent series means you also diverge. Let's take these convergence tests and apply them to some examples. Determine whether or not the sum of 2 to the I over I squared plus 3 to the I converges or not. Well, we're going to let a sub I be exactly the terms of the series we have in this problem, 2 to the I over I squared plus 3 to the I. We're going to let b sub I simply be 2 to the I over 3 to the I. So since the absolute value of 2/3 is less than 1, if I was to attempt to just take the series of bi, I would just be adding up 2/3 to the I. That's less than 1 to the I. That's a geometric series, and by the geometric series test, we conclude that the series formed out of bi converges. But observe as well that ai and bi are all non-negative, but ai is strictly smaller than bi because ai has 2 to the I over 3 to the I, but the denominator is only bigger. So ai is only smaller. So since we determined that the sum of bi converges and ai is smaller than that, by the comparison test, the series out of ai also converges. So the series we began with, the sum of ai, does converge. One thing to point out is I happen to know that if I add up the bi, because it's a geometric series, I get exactly what it converges to. The sum of 2/3 to the I converges to exactly 3. However, the sum of ai, I can't really say what it converges to. It must converge to something smaller than 3, because I was adding up things less than or equal to this, and the bi's added up to 3. So while I do know the sum of ai converges, and I know it converges to something less than or equal to 3, other than that, I really cannot say exactly what it sums up to. As a second example, let's determine whether or not this series converges. I squared plus 3 over I to the 4th minus 2I cubed plus 39. Well, if we go ahead and set ai to be the sequence that we are adding up here, and bi to simply be 1 over I squared, then the limit of ai over bi is 1. This is why I picked bi to be I squared, because a sub I is fundamentally determined by its biggest powers of I squared over I to the 4th. So more or less, we expect a sub I to behave like I squared over I to the 4th, which is just 1 over I squared. And the way we formalize this is by showing that the limit of ai over bi is 1. And that's a fairly quick computation once you know how to compute these limits. Now, since the terms of our sequence are non-negative and this limit is a finite number, the limit comparison test tells us either both series converge or both diverge. But the sum of bi is convergent by the p-test. We're adding up 1 over I squared, so p is 2, that's bigger than 1. Therefore, our series of ai is also convergent. As a third example, determine whether or not the sum 2 to the I divided by I squared converges. Let's let a sub I be exactly what we're summing up here, 2 to the I over I squared. We're going to let b sub I be 1.5 to the I. Now, if I tried to take a series of 1.5 to the I, that would be a geometric series where the common ratio was 1.5, which is bigger than 1. So if I sum up bi, that diverges by the geometric series test. However, it is possible to show that a sub I over b sub I goes to infinity. By the limit comparison test then, since this limit is infinite, we conclude that ai is generally bigger than bi because this ratio goes to infinity. So ai is larger than bi, but the sum of bi diverges and ai is even bigger than that. So the series formed out of the ai should also diverge. Notice, however, if we had set b sub I to be 2 to the I, then the ratio of ai, 2i over I squared, over 2 to the I, if we had put a 2 here, would have been 1 over I squared, and that would have had limit 0. If this limit is 0, okay, then there's limited information you can get. That just tells me that ai is generally smaller than bi, but then the sum of bi going to infinity would just tell me that ai is smaller than something divergent from which I cannot get any information at all. So if we had set bi equals 2 to the I, we would not have been able to conclude anything. Overall, what did we accomplish in this quick little review? Series are formed by adding up terms of a sequence, but formally what they are is a limit of finite sums. We have lots and lots of tests to determine whether a given series converges or not, and in this video we covered the geometric series test. A geometric series, some constant times r to the I, converges if and only if the absolute value of r is less than 1. The series 1 over I to the p converges if and only if p is larger than 1. If the limit of a sequence is not 0, then the series formed out of it diverges. The comparison and limit comparison tests also provide ways to use simpler series, like the examples we did before. Okay, in our examples, we had slightly more complicated series, but we used comparison or limit comparison tests to compare the series we had to something simpler, like a geometric series or a p-series.